Welcome back to our channel. Today we have a continuous beam that is supported on 4 supports, and in this case every span is loaded with a uniformly distributed load. We are expected to plot the BMD as well as the SFD for this particular beam. So the BMD we are going to plot it here, and the SFD we are going to plot it here as well. Now we are going to begin with calculating the maximum bending moments at every single span. So we have span AB, span BC, as well as span C to D. So we are going to begin with span AB. So for span AB, the maximum bending moment will be given by W1 L1 squared divided by 8, since that span is loaded with a UDL, and that's the formula of getting the maximum bending moment between that span. And this is going to be W1, which is 2 kilonewtons per meter, multiplied by the span over which it is distributed, that is 6 squared. We divide that by 8, and that's going to give us 9 kilonewtons meter, 9 nkm. Then we go to the span B to C, the span BC. And for the span BC, the maximum bending moment is also going to be given by this formula, W2 L2 squared divided by 8, which is going to be W2 is 1 kilonewtons per meter, L2 is 12 meters, we square it, and then we divide that by 8. That's going to give us 18 kilonewton meter, 18 kNm. Finally, we are going to consider the span C to D. So the span C to D, the maximum bending moment will be given by W3 L3 squared. We divide by 8, which is going to be W3 3 kilonewtons per meter. The span CD 4 meters, we square it, and then we divide by 8, and that's going to give us 6 kilonewtons meter, 6 kNm. Then we are going to plot the bending moment diagram due to this uniformly distributed rods, starting with the span A to B, then we have C, D. So for the span AB, we have 9 kilonewton meter. So 9 kilonewton meter, let me approximate it about that point, and that is going to be a smooth curve, because it is a UDL, so we have 9 kilonewton meter. Between B and C, we have 18, so let 18 be approximately there. It is also a smooth curve, because that is a uniformly distributed rod. So here we have 18 kilonewton meter. Then finally, we have the span C to D, 6 kilonewton meter, approximately there. So we also plot a smooth curve having a bending moment of 6 kilonewton meter. Good. After we have done with plotting the bending moments diagrams, the next operation will be calculating the area of each bending moment diagram, as well as the center of gravity from the center of gravities of these BMDs from the span A, from the span D, or wherever. So we begin again with the span AB, and in this case, for span AB, A1, that is the area of this bending moment diagram, will be given by 2/3 of its base, and its base A to B is 6 meters, multiplied by its perpendicular height, which is 9 units. So we multiply by 9, and that's going to give us an area of 36 square meters. 36 square meters. Then bar x1. Bar x1 is the distance from the center of gravity of this bending moment diagram all the way to the end A. So that is bar x1. Bar x1. And bar x1 will be given by half the span A to B, which is a half of that span, which is 6 meters, and that's going to be 3 meters. From there we go to the span for span B to C. So for span BC, we are going to have A2. A2, that is the area of this bending moment diagram between the span B and C, which is going to be given by 2/3 of its base. The base is the span B to C, that is 12 meters, multiplied by the perpendicular height, which is 18 units, which is going to be 144 square meters. 144 square meters. Then we need bar x2 from the support B. From support B. And bar x2 from support B is the center of gravity of this bending moment diagram to the support B. So that is bar x2 from the support B, which will be 12 meters. We divide by 2, which is 6 meters. We also need bar x2 from the support C. So from the support C, the distance of the center of gravity, that is bar x2 again, from the support C, is also going to be given by half of span BC, which is 12 divided by 2. It is 6 meters as well. So we are done with the span B to C. And finally, we are going to consider the span CD. So for the span C to D, the area of this bending moment diagram, that is A3, because it is the third bending moment diagram, that will be given by 2/3 of its base C to D, which is 4 meters, multiplied by its perpendicular height, which is 6 units. And that is going to give us an area of 16 meters squared. So we have 16 square meters. 16 square meters. Bar x3. Bar x3 is the distance from the center of gravity of this bending moment diagram all the way to the end D. So that distance is bar x3, which will be given by half of that span, that is half of 4, which is 2 meters. So that is the value of bar x3. Very good. So after that, we are going to apply the three-moment theorem, or the Clapeyron's equation of three moments, which states that, so we are going to begin with the spans AB and BC. So for the spans AB and BC, the three-moment theorem will state that MA L1 plus 2MB into bracket L1 plus L2, we close the bracket, plus MCL2 will be given by 6A1 bar x1, divide this by L1, plus 6A2 bar x2, divide that by L2. Now in this case, the end supports are the bending moments at the end supports are going to be 0. And that means that the bending moment at A will be 0. Therefore, MA is equals 0. And we are going to have this 2MB into bracket. L1 is 6 meters. L1 is the span A to B, L2 the span B to C, and L3 the span C to D. Therefore, we are going to have L1 6 meters plus L2 12 meters plus L2 MCL2, which is 12 MC, being equal to 6 multiplied by A1, and we have A1 is 36 square meters, so we multiply that by 36. We multiply by x1, which is 3 meters, and then we divide that by L1, which is 6 meters. We add 6 times A2, which is 144 square meters. We multiply that by x2, which is 6 meters from the support B. So we multiply that by 6. Divide by the span L2, which is 12 meters. 12 meters. So this is going to be 6 times 12, that is 18. 18 times 2, that is 36. So we are going to have 36 MB plus 12 MC, which will be equal to 6 times that 6 times 3 over 6, that is 108, so is equals 108 plus 6 times 1, 44 times 6 divided by 12, that is 432. This is going to lead us to 36 MB plus 12 MC being equal to 108 plus 432 is 540. Then we are going to simplify this equation by dividing through by 12. So 36 divided by 12, that is going to be 3 MB plus MC, which will be equal to 540 divided by 12 is 45. We divide that by 45. We can make MC the subject, which will be MC will be given by 45 minus 3MB. So we are going to call this equation 1. So that will be our equation 1. Then from there we go to the span C to D, the span BC, and C to D, the span BC and CD. And we are going to, applying the 3-moment theorem, we are going to have this MBL2 plus 2MC into L2 plus L3 plus MDL3. That will be given by, let me write it down here, 6A2 bar X2, divide this by L2, plus 6A3 bar X3, we divide this by L3. Now, as we had said earlier, the bending moment at the end supports is equal to 0, and therefore the bending moment at D is also equal to 0. So we are going to remain with MBL2, and L2 is 12 meters. Therefore, 12 MB plus 2MC into bracket L2 plus L3. L2 is 12 meters. L3 is 4 meters. Plus MDL2 L3, and MD is 0. Therefore, we are going to have equal to let me write these values down here. We are going to have 6A2, and A2 is 144 square meters. Therefore, 6 multiplied by 144 multiplied by L by x2, that is 6 meters. Then we divide this by L2, which is 12 meters. And then we add 6 multiplied by A3. A3 is 16 square meters. Multiplied by x3, which is 2 meters. And then we divide that by L3, which is 4 meters. And that's going to give us 12 MB plus 12 plus 4, that is 16. 16 times 2, that is 32. So plus 32 MC, which is going to be equal to 6 times 144 times 6 divided by 12, that is equal to 432. So is equals 432 plus 6 times 16 times 2 divided by 4, that is 48. So we add 48. And this is going to lead us to 12 MB plus 32 MC, which will be equal to 432 plus 48, that is 480. So that is equal to 480. Then we are going to divide through by 4 to simplify this equation. So 12 divided by 4, that is 3. Therefore we are going to have 3 MB plus 32 divided by 4, that is 8. So 8 MC is equals, this one when you divide by 4, that is going to be 120. So this is going to be our equation 2. Good. Now from there, we are going to have this. Now we said that there's somewhere we said that equation 1, MC is 45 minus 3 MB. Therefore, this MC, we are going to substitute it here. And this is going to give us 3 MB plus 8 MC. And MC is 45 minus 3 MB. 45 minus 3 MB being equal to 120. So that is equals to 120. And it's going to give us 3 MB plus 8 times 45, that is 360, minus 8 times 3 MB, that is 24 MB, is equal to 120. 3 MB minus 24 MB, that is minus 21 MB. Minus 21 MB is equals to, we take 360 the other side of the equal sign, that's going to be 120 minus 360, and 120 minus 360, that is going to be minus 240. So definitely this negative and this one will cancel out, and therefore you are going to have 21 MB is equals 240. We divide both sides by 21 to get the value of the bending moment at B, and that is going to give us a bending moment at B of 11.43 kilonewton meter. So that is the bending moment at the support B. Bending moment here at the support B. Then we come back where? We come back here to determine the bending moment at C. since we now have the bending moment at B. And we are going to have MC now will be given by 45 minus 3MB, which is 3 multiplied by 11.43, and that is going to give us a bending moment of 45 minus 3 times 11.43, that is 34.29, and that is going to give us a bending moment at C of 10.71 kilonewton meter. So that is the bending moment at C. Bending moment at C. Very good. After getting the bending moment at all the supports, bending moment at A is 0, bending moment at B 11.43, bending moment at C 10.71, and bending moment at D, which is 0. We are going to plot the bending moment diagram, and we are going to plot it like this. Bending moment at A is 0. Bending moment at B is 11.43, and 11.43 is just somewhere above 9. Let's approximate it at that point, and then we join it there at B. Bending moment at C is that is C 10.71, just some few units below this 11, so we join it there. And then bending moment at D is 0, so we are going to drop this line and join it to D. So we are going to write here the bending moment at B 11.43 kilonewton meter. Then here we have 10.71 kilonewton meter. So let me adjust this 6 kilonewton meter and write it here 6 kilonewton meter. Good. So this is a positive bending moment. This is a negative bending moment, because the bending moment at a support B and support C are going to be negative, since that beam is going to be hogging when it bends and sagging when it bends between A and B. The bending moment here is positive, this bending moment is negative, whereas this one is positive. Then from there we can shield it off. So ladies and gentlemen, that is what we call a bending moment diagram. Therefore, for us to plot the shear force diagram, we must first of all calculate the reaction. So we go to reactions, calculations, and on reaction calculations, we are going to begin with the span CD, and in this case we are going to take moments about C. Therefore, for span CD, we take moments, taking moments about C, taking moments about C, we are going to have the following. So we are going to have RD times the distance from D to C, and that's going to be RD times the span D to C is 4 meters, plus we add the reaction, we add the bending moment at C, which is 10.71, because those two are going to be anti-clockwise moments. So we add 10.71 kilonewtons is equal to this clockwise moment, 3 kilonewton per meter, multiplied by its span, which is 4 meters, that is converting the UDL to point rod, and then it is going to act at the mid-span of C and D, which is 4 divided by 2. So this is going to be RD times 4, which is going to be equal to This is the 3 times 4, that is 12. 12 times 2, that is 24. So is equals 24. Then we take this 10.71 this side of the equal sign, that's going to be minus 10.71. And the reaction at D is going to be 24 minus 10.71, that is 13.29. So 13.29, we divide that by 4. And when we do that, we are going to get a reaction at D of 3.32 kilonewtons. Therefore, reaction at D is 3.32 kilonewtons. Good. From there, we go to the span AB. Therefore, for span AB, that is this span, taking moments about B, taking moments about the support B, we are going to get what? So this is going to give us RA times 6, taking moments about B, that is a clockwise moments. Therefore, RA times 6 plus the bending moment at B, which is 11.43 kilonewton meter. 11.43 is equal to this clockwise moment, anti-clockwise moment, I mean 2 kilonewtons per meter UDL times the span over which it is distributed, 6 meters, that is converting it to point rod, which will act at the mid span of B and D, of A and B, sorry, which is 6 divided by 2. And this is going to be RA times 6 is going to be equal to 6 times 6, this 2 and this one we cancel out, 6 times 6, that is 6, minus taking 11.43 the other side of the equal sign, and 36 minus 11.43 is 24.67. So we are going to have RA being equal to 24.67. We divide by this 6, that is going to give us a reaction at A. Reaction at A of 4.095 kilonewtons. So that is the reaction at A. To get the reaction at B, we are going to take moments about C. Therefore, taking moments about C from A, we get, so we are going to get the following: RA times the distance from A to C, which is 18 meters, therefore RA times 18 meters, plus RB times the distance from B to C, which is 12 meters, plus RB, these are clockwise moments, RB times 12, plus the bending moment at C, which is 10.71 kilonewton meter. So we add 10.71 is equal to, between A and B, we have a UDL of 2 kilonewtons per meter. Let me write it down here. So we are going to have 2 times the span 6 meters times the distance from the midpoint of this AB, which is going to be 6 divided by 2, and then we add the distance from B to C, which is 12 meters, plus 12. Then we add, between B and C, we have a UDL of 1 kilonewtons per meter. We multiply by the span over which it is distributed, and then it is going to act at the mid span of B and C. So this is going to give us RA times 18 plus RB times 12 plus 10.71 being equal to 12 times 15, which is 180. So we have 180 plus these two, 12 divided by 2, that is 6. 6 times 12, that is 72. So we add 72. Now, in this case, the reaction at A, we have it, which is 4.095. So we are going to have 4.095 times 18 plus 12 RB plus 10.71 is equals 252. 4.095 times 18, that is 73.71. So you have 73.71 plus 12 RB plus 10.71 is equal to 252. 252. Very good. So this is going to be 73.71 plus 10.71. That is going to be 84.42. So we have 84.42 plus 12 RB. 12 RB is equals 252. 252. So we are going to have the reaction at B being equal to 252 minus 84.42. We divide by this 12. So we are going to have RB is equals 167.58. 167.58 we divide by 12. And that is going to give us a reaction at B, 13.965 kilonewtons. So that is the reaction at B. To get the reaction at C, we are going to say this, that the sum of all the upward acting forces must be equal to the sum of all the downward acting forces. And in this case, the upward acting forces, we have RA plus RB plus RC plus RD is equal to the downward acting forces. We have the three UDLs. We convert them to point rod. Span AB we have times 6. Span BC we have 1 times 12. And the span CD we have 3 times 4. 3 times 4. Reaction at A. Reaction at A is 4.095. So we are going to have 4.095 plus reaction at B, which is 13.965 plus reaction at C plus reaction at D, which is 3.32. So we add 3.32. We equate that to 2 times 6, that is 12 kilonewtons. 1 times 12, that is 12. 3 times 4, that is 12. So when we add 4.095 plus 13.965 plus 3.32, that's going to give us 21.38. So 21.38 plus RC is equal to 12 plus 12 plus 12, that is 36. So the reaction at C will be given by 36 minus 21.38, and that is going to be a reaction of 14.62 kilonewtons. So ladies and gentlemen, those are the values of all the reactions that we need. The next thing will be shear force calculations, and we are going to begin with shear force at the end D, and the shear force at the end D is going to be equal to this reaction at D, which is 3.32 kilonewtons. Then from there we have shear force between D and C. It is going to change uniformly from 3.32 kilonewtons minus the UDL between D and C, when you convert it to point rod, that is going to be 3 times 4, which is 12. So we subtract 12, and that is going to give us negative 8.68 kilonewtons. Then from there we go to shear force at C, and the shear force at C will be this negative 8.68. we add the reaction at C, which is 14.62, and that is going to be 5.94 kilonewtons. From there we go to shear force between C and B. The shear force between C and B, it is going to change uniformly from this 5.94 minus, between C and B we have a UDL of 1 kilonewtons per meter. When you convert it to point rod, we multiply it by 12, that is going to be 12. So we subtract 12, and that is going to give us negative 6.06 kilonewtons. Then from there we go to shear force at the support B, and shear force at the support B is going to be this negative 6.06. we add the reaction at B, which is 13.965, and that is going to be 7.905. So we have 7.905 kilonewtons. So that is the shear force at B. Then you go to shear force between B and A. So we go to the shear force, just going to write it down here. Shear force between B and A. The shear force between B and A will be this 7.905. We subtract the UDL between B and A, which is 2 kilonewtons per meter. When we multiply by 6, we are going to convert it to point rod. So that is going to be 2 times 6, which is 12. And the shear force between B and A, that is going to be negative 4.095 kilonewtons. So those are the values of the shear forces. Finally, the shear force at A is also going to be equal to 4.095. After getting all the values of the shear forces, we are going to use those shear force calculations to plot the shear force diagram. Good. Plotting the shear force diagram, we come here, we are going to begin with this end. So we have the shear force at D. So the shear force at D is 3.32 kilonewtons, approximately that point. So we are going to drop it there. So we have 3.32 kilonewtons. Then shear force between D and C will change from 3.32 to negative 8.68. So negative 8.68, let me approximate it to be at that point. We join those 2 points together. So this is 8.68 kilonewtons. Join it to the horizontal line. Then shear force at B, shear force at C, sorry. Then shear force at C, that is 5.94. Let's approximate it to be there. So that is the shear force at C, which is 5.94 kilonewtons. Shear force between C and B, which change from 5.94 to negative 6.06 below this line. So negative 6.06, let's approximate it there. Then we join those 2 points together like that. So this is negative 6.06 kilonewtons. Join it to the horizontal line. Then the shear force at B, that is 7.905. Highest point here or here, so that we get a space to write. So we are going to join it to the horizontal line. So this is 7.905 kilonewtons. Then the shear force between B and A changes from 7.905 to negative 4.095. So negative 4.095 approximately there. So we join that to 4.095, 4.095 kilonewtons. Finally, we join the shear force at A is also this. We join it that point. So this is a negative shear force, positive shear force, negative shear force, positive shear force, negative shear force, positive shear force. Remember, all the positive shear forces should appear above this horizontal line, and all the negative shear forces should appear below this line. Finally, we are going to shade off the outline so that our diagram becomes clear and clear. So let me shade it off. Yep, so that is our shear force diagram. So, ladies and gentlemen, thank you very much for being here once again to watch our video, and please remember to subscribe and hit the notification bell as well, so that whenever we upload a new content, you will always be the first person to be notified. So thank you very much, all the supporters and all our subscribers. Let's meet in yet another lesson.